Looks like we're live. Hello and welcome to another Zozin session. How about that? So, excuse me, today we continue developing our programming language called Porth, and the source code of which you can find in the description if you're watching on YouTube, and if you're watching on Twitch, you can find it in the chat. Hello everyone in the chat. Hello Zaylin, Ep.17 entry, Biter Broad, I Good Duke, hello, really glad to see you all today. So I'm gonna put the source code to this thing in the description, right? So this is the source code, there we go. And we've been developing this thing for quite some time, so we accumulated a playlist of the episodes of the development of this language. You can find the playlist in the description as well. If you go to the Debugging daily channel, so here is the playlist. Yep. K Dominic, subscribed with 2 months. Hello. Thank you so much for 2 months of Twitch Prime subscription, and welcome to our Epic Porth Club. How about that? Hello Crazy Chicken, hello Young, Deeps, subscribed with Twitch Prime, your first subscription by the way, and welcome to our Epic Porth Club. Okay, so Porth development playlist, not player list, playlist, and if you're watching on Twitch right now, you can actually get the link in the chat. I'm gonna post it in the chat. So we've been developing this thing for quite some time, and this thing is capable of you know, pretty cool stuff. So let's actually fetch the latest things. All right, so let's go to the master and straight up fetch everything. Hello everyone, welcome. All right, so merge origin master, there we go. So maybe I should actually do tmux super quick. This in Porth. There we go. So the language is, if you follow the series, you know that language is written in Python and it is interpreted and compiled. Right, so and the way we compile things is by generating assembly and then piping the assembly to NASM. So we've got some bits, just a second. To the Prime donated 200 bits, thank you so much for 200 bits. And Lazy Greed subscribed with tier 1 subscription for a month. Thank you so much. Thank you for all the support. Hello everyone, really glad to see you all today. So yeah, essentially it just generates assembly and then using NASM, right, NASM, it compiles it to a final executable. And NASM is one of the famous x86-64 assemblers. I'm gonna put the link to this thing in the description if you are interested. So assembler we use, right, so this is the one. So another thing that we could have used is FASM, and I don't have any particular reason to not use flat assembly. It's just like I'm familiar with NASM rather than FASM, so that's why I'm using it, right? So it's like not really even a preference, it's just like I happen to know NASM and I don't know FASM, so that's why I'm using NASM. So yes. So and how would you write something like a hello world in such language? Right, so let's take a look. Let's take a look at some simple examples of something. Hello.porth. First of all, you need to include the standard library, right? stdporth. And then you put a string literal, hello world. And recently we introduced a convenience function which prints a string on the standard output. It's called puts, right? And this is it. This is the hello world in this language. And the reason is why the order is so weird is because it's a stack-based language, right? It's a stack-based language, and the stack-based languages, they usually use reversed Polish notation. So if you want to learn more about this kind of stuff, you can search stack-oriented programming. I think that's the best way to describe that. So yeah, there is a Wikipedia article about that. Stack-oriented programming is another thing. It's called concatenative programming. Right? Concatenative programming. What's interesting is that it's pretty much the same thing, but it's two separate articles. I suppose stack-oriented programming is a form of concatenative programming, if I understood correctly. So from what I can see, concatenative programming is a more general term, and stack-oriented programming is basically one specific instance of that. In any case, I'm going to post both of the links in the description, so I don't really know what's exactly the difference, right? So, but you can read both of the articles and maybe tell me in the comments what's the difference between concatenative programming and stack-oriented programming. So, yesu. And essentially, yeah, that's why we first sort of push the string onto the stack, and then we print that string to the standard output, right? And as I already said, it can be interpreted. You can basically simulate the entire thing, and as you can see, it says hello world, and it didn't even put any new lines, so let's actually put a new line in here, right? There we go. And it can be also compiled, and when you try to compile this entire thing, look, it generates hello.asm, right? And it's actual file that you can like look at. So this is where it starts, and it basically translates a bunch of instructions of the language into assembly code, right? And then what it does, it compiles this asm file into an object file, and then links that object file into a final executable. So here we have a final executable that we can take a look at. It's ELF64-bit least significant byte executable, and it's statically linked. As you can see, we don't even link with libc. We don't really depend on anything, and we can even confirm that by using LDD. Right, there we go. It's not a dynamic executable, and if you try to execute this entire thing, it will say hello world. So even though this thing is written in Python, it's a native statically typed language, right? It's a native statically typed language, and we're using Python basically as a bootstrap, right? We're using it as a bootstrap. So you can actually do more complicated stuff in this language. In fact, there is a whole folder called examples. Right. So again, you can get the source code of this thing in the description. If you are in the chat, you can do project command and it will give you the link to this thing. And here is the folder called examples. And I really recommend to check out some of the examples in here just to get the gist of what language is capable of. Right. So one of the recent interesting examples that I implemented is a game of life. Right. So I already proved some time ago, demonstrated that this language is Turing complete by implementing Rule 110. Rule 110 is a cellular automaton that is usually, like I personally use as a way of demonstrating that my language is Turing complete. So if you're interested about this kind of thing, you can just Google it up, Rule 110. There is a description on Wikipedia, of course, right? So, and I'm going to post it in the chat, and also I'm going to put the link to Rule 110 in the description. So here it is. And let's take a look. Examples, Rule 110 Porth. I'm going to compile it, right? So I'm compiling this entire thing. As you can see, it compiled, and then I can try to run it. And as you can see, it generated Rule 110 pattern, demonstrating that the language is in fact Turing complete. So, but recently I implemented even cooler example, game of life. So it's located in goal.porth, and it's not just like a game of life that basically prints the state of the game on each separate like line, right? It's not like that. It's actually interactive in some sense, right? It looks like this. Right, so essentially it uses terminal escape codes to redraw itself, right? So you can actually stop it, and you see you can do whatever you want. Basically, it's almost like C. So it's at the same level as C. You can do whatever you can do in C, you can do in this language, right? So it is already pretty powerful. It is already pretty powerful. So that's pretty cool in my opinion. Right. And we had a lot of plans for this language, so let's take a look at what kind of plans we had for this language. So I wanted the language to be compiled. It is in fact compiled. I wanted it to be native. It is in fact native. As you can see, I already demonstrated that it produces native executables. I want it to be stack-based, just like Porth. Well, it was stack-based since day one. I want it to be Turing complete. I demonstrated Turing completeness by implementing Rule 110 and Game of Life and so on and so forth. It is Turing complete. I want it to be statically typed. It is in fact statically typed, so not all of the programs can easily compile, for example, hello world, if you instead of string provide a number, it won't work as far as I know. So if you do something like this, compile hello Porth, yeah, so not enough arguments. Essentially, string expands into two values. It expands into the size of the string and the pointer to the beginning of the string. So, and since you didn't provide the string and provided only the number, Puts complains that you didn't provide enough arguments. So as you can see, we have sort of like a compilation type checks on the entire code, right? So the code that doesn't make any sense, it won't compile, essentially, it's statically typed. And essentially, for instance, if you have conditions, you cannot just put 10 into the condition, right? You can only put boolean, right? As you can see, invalid argument, expected boolean, and the only thing you can do in here is like something like this, only that will compile. But yeah, and also the block itself is not allowed to modify the stack, so if there was nothing before the stack, it should stay nothing, so we have to consume this entire thing, and only then it will compile. As you can see, we statically check everything. So we pretty much, you know, fulfilled all of the plans, and the only thing that is left, is making this compiler self-hosted. What self-hosting means? Self-hosting means that the compiler is written in itself, right? It is written in itself. And I think the language reached the point that it is possible to rewrite this language in itself. And that's exactly the topic of today's stream. That's precisely the topics of today's stream. And today we're going to at least start rewriting language in itself, right? We're only going to start. Of course, we're not going to do that in one sitting, because the language itself it's not really that complicated. It's not as complicated as like real production languages, but it's like almost 2,000 lines of Python code, right? So when we need to sort of translate that to Porth. And of course, not everything that is implemented here can be easily translatable to Porth. We're going to find a lot of problems, a lot of bugs that we're going to fix along the way, maybe missing features. Maybe while implementing Porth, we'll realize that we're missing some features, so we'll have to go back to Python version and implement that feature, and then go back and implement it in Porth. So it's going to be quite the journey. It's going to be quite a journey, trust me. So yeah. About that, are you guys ready to, you know, start this beautiful, beautiful journey yet again? Because we're basically going back and starting the same thing from scratch in a different language in itself. Right. So, and I think we got rated. We got rated by Strawberry Hacker. Thank you so much for the rate. And everyone, if you never heard about Strawberry Hacker, I really recommend to check out their Twitch channel, twitch.tv/Strawberry Hacker. They're developing a lot of cool things like operating system, programming languages, and stuff like that. So, I really recommend it. All right, so let's go ahead and do that. So we have a bunch of stuff that I probably want to just get rid of. Clean FDX. So self-hosting, right? So this is going to be a separate branch, and as you can see here, we have porth.py, and the time has come to create a file called porth.porth, right? Because the extension for our language is Porth, so it's a porth.porth file. So this is going to be the official source code of the compiler. Right. The first thing we want to do, I suppose, we want to include the standard library, right? So we want to use the standard library. And to set ourselves for success, I don't know, we can write a hello world. We can try to write a hello world like this. Hello world is actually not really that interesting. Let's actually write some sort of a to-do. So recently I introduced a very interesting intrinsic called here, right? It's a very interesting intrinsic. So it basically aliases to a string. It aliases to the string. So if you try to print the string, this is how it's gonna look like. So let's actually do Porth, simulate Porth.porth, right? So it aliases to this string. Look. So it aliases to the file name where here is located, then the row at which here is located. I can actually change the row, and as you can see, the row has changed, and the column at which this thing starts. Right. So, and you can use this thing to implement like rudimentary asserts or command line or to do things, right? So essentially after you put here, you can put something like to do implement Porth in itself, right? And you can do puts again, and then you can exit with non-zero exit code, right? And if you try to execute this entire thing, as you can see, it complains implement Porth in itself, and Emacs can parse that, and it allows you to jump in here. So yep. So maybe this is going to be the first to do that we're going to add to the Porth. So so it's pretty much nothing, but we already set ourselves for success. So let's go ahead and start implementing everything. So in our language, we have different operations. Let's start with the very simple operations, right? So we're gonna have like operation codes for the operations. Does it make sense? Operation code for the operations? Maybe it does make sense. So the first operation that we want to be able to perform, we want to be able to push integer onto the stack. So the code for this thing is going to be 0. Unfortunately, our language doesn't have enumerations or anything like that, so we'll have to maintain these things manually. It's a pretty, you know, Spartan language, I would say, but I think it is possible to re-implement it in itself. We'll see how it goes. Again, if we'll encounter some lack of features, we can always just go ahead, like go back to the Python version and implement that feature there, and then continue the development, right? So, but we have to keep in mind that every time we add a new feature, re-implementing Porth in itself becomes a little bit more difficult. Like think about it. You re-implementing Porth in itself, and you're missing a feature. And if you add that feature, you also adding yourself more work while re-implementing Porth in itself. So every time you want a feature and you implement it, you actually pay for it with longer re-implementation. It's actually very interesting. So it's always like, do I want to have this feature? But if I add that feature, that will make it more difficult to implement. Right? So you don't want to overcomplicate the language to the point where it becomes difficult to re-implement in itself. So it has to be some sort of like, you know, balance. I don't even know, like, and how to find that balance. It's very interesting. And I never implemented languages like self-hosted languages, so I don't really know what to expect. So I'm really curious what we're gonna you know, encounter here. Anyway, so another operation that I want to be able to do after we push some numbers, we want to do something with the numbers. So I want to be able to sum them up, right? So I want to sum up those numbers. And I guess last operation that I want to be able to do, I want to be able to print whatever is at the top of the stack, right? So these are the main intrinsics, or rather operations. We don't have a concept of intrinsics yet that we want to be able to do, right? So, and we also need to store the operations somewhere. We're going to be storing them in a memory. So we need to store them in some sort of a structure, right? We need to store them in some sort of a structure, but we don't have structures in the language, again, because we can add them, but then it will be more difficult to re-implement language in itself, right? So because of that, I don't really want to add them yet. I don't want to add them yet. So let's actually do all of the memory layouting ourselves manually, right? So what we're gonna assume, so the size of the structure OP, how is it gonna look like? So let's actually imagine that we have a struct, and here we're gonna have a type, and let's say that the type is gonna be U64, right? So, and this is precisely the type, right? So this is precisely the type. And then we're gonna have an operand, and it's gonna be U64 as well. So this is basically the definition of the structure. And essentially for plus and print, the operand is going to be 0, And only for the integer, the operand is going to be the value that you want to push onto the stack, right? And in the memory, we're going to just store the array of these operations, right? So we have a special intrinsic called memory. It gives you the pointer to the beginning of the memory from which you can do things, right? So you have a reserved chunk of memory that you can just use for whatever purpose. And we're going to store everything there. So the first thing I want to do, I want to have a variable that stores the amount of operations that we have, something like ops count. And I want this thing to start at the beginning of the memory, right? So I'm going to create a macro and I'm going to point ops to the beginning of the memory, right? So then I want to have a pointer to the beginning of the array of the operations. So I want the array of the operations to start after the amount of operations, right? So that means I need to do something like ops count. I need to take ops count and add 8 to it, right? And that is basically the pointer to the beginning of the operation array. There we go. So I have two things like that. So if you want to allocate memory, you usually do it like this. Again, it's pretty stupid, it's pretty dumb, but it's easy to implement. And that's why we're doing it this way. Right, so maybe it's not going to be enough, we'll see, all right. So what I want to be able to do, I also want to be able to have like some sort of operation called push OP, right? Push OP that accepts you know, the type and the operand and just adds this OP to this array, right? So I want to have something like this. So the implementation of this thing is going to be right now outside of the scope. So I'm going to do something like push OP is not implemented yet, right? So, and I'm going to end this thing in here. So maybe I'm going to put this definition somewhere here. There we go. So, and after that, let's actually write some sort of a program, like a simple program. Push integer OP, push integer. And what kind of integer we want to push there? We want to push 34, and it's going to be push OP. Right, there we go, push OP. The second one we want to push is 35. After that, we want to sum it up. So plus doesn't have any operand, right? So, and that's why it's going to be 0. And then we want to print the result on top of the stack. So here we're going to have like a simple hard-coded program, right? Hard-coded program. All right. So after that, we should probably just basically either simulate that thing or interpret it. Right. In fact, we may actually do something like this. So let's actually create a program called simulate OP, and we're going to put a to-do in here, right? Simulate OP is not implemented yet, and we're going to end it like that. And actually OPs, right? Because there are several of them. And another one is going to be compile. Compile OPs is not implemented yet. So the question is, which one do we want to implement first? I kind of want to implement first compile operations because it is easier. Essentially what we have to do, we have to iterate through all of the operations in here and just write chunks of assembly when we encounter them. And that is basically it. So compilation is easier to implement than simulation, because in simulation we'll have to allocate like a stack for which we're simulating and so on and so forth. So I want to start with the compilation, right? So I think it's going to be a little bit easier to implement. So, right, yeah. So let's go ahead and do compile ops. Compile ops. Okay, so if I try to do that, it complains. Oh, this is because push OPs accepts two things. Let's actually drop them like so, and push OPs is not implemented yet. Okay, so this here intrinsic is actually extremely useful, right? It lets you actually just, you know, jump to the place, and yeah, it's actually super convenient. All right, so we need to push a specific operator onto the stack. Does anyone have any questions so far, by the way? Anyone know how this code is to be interpreted? Does it transpile to something else, intermediate representation, AST route, to another bytecode, and ultimately binary? I actually explained it at the beginning of the stream, so you may want to actually rewind back and watch the explanation, but essentially we have two modes. The simulation mode, which just, interprets this entire thing. We don't have AST because it's concatenative language. We don't have any AST, so we just interpret it as it is. And the second mode is compilation mode. And compilation mode generates assembly code as a text and pipes it into NASM. And this is how we compile. On top of that, you may want to take a look at the source code of the project. It's completely open source. So is there shifting like in C? Yes, there are intrinsicals SHR and SHL that allows you to shift left and shift right. And we do use them quite a lot in Rule 110 implementation. And for, different capabilities of the language, I recommend to take a look at the example folder. So there's some examples implemented in this language. All right, so thank you so much for the bits. I saw somebody actually gave me bits. Thank you. I really appreciate that. All right, so we're pushing the operation. Okay, so first we need to figure out where exactly we want to push the thing. So I'm gonna go and just do ops count. That puts ops count onto the stack, right? And I want to actually dereference this entire thing, so I'm gonna do 64. Yeah, so that dereference this entire thing, and after that I want to multiply this thing by the size of the structure, right? So I need to take a look at the end of the ops array. So so I'm gonna go ahead and push size of OP, and I'm gonna multiply by it. So this entire thing is basically multiplied by size OP, right? So this is what we have on top of the stack. And as I already said, OP is gonna be defined like this, and the size of this entire thing is gonna be 8 plus 8 is gonna be 16. So let's actually go ahead and define a macro size of OP, 16. By the way, there is no special characters in this language, like at all, except maybe for quotes. Quotes kind of mean the start and end of the string, and also single quotes mean the character. Apart from that, there is no special characters. So if you want to define a macro with special characters, you just defined this macro. You can use this name. And yeah, that's why I can define something like this. This is a single word. Right, you can use whatever characters you want in your macro definition. So it's not a part of the syntax, actually. These parentheses are not part of the syntax. So that way I can sort of make up syntaxes, right? So I can make it up like it's non-existent. So yeah, I could have actually called it size of OP, but that would be kind of boring, I think. I think that would be kind of boring. So I decided to call it like that. So I think it looks a little bit better, right? I think it looks a little bit better. All right, so here I have basically the offset that I have to add to the beginning of the array. So I have to push OPs to here, and I have to add this entire thing to here, right? So, and that way I've basically got the pointer to which I have to add the operand and the rest of this stuff. So this one is rather interesting. So what's going to be the easiest way to add that? Operand has to be added after, so it's the second thing in here. All right, so let's actually duplicate this entire pointer, right? So maybe I'm gonna just rename it to a pointer, and I just duplicated it in here. There we go, I just duplicated it. Maybe one of the things I want to do, I want to offset it by 8, so I'm going to do 8 plus, right? So this is plus 8, and here is the different things that I basically have in here. So this is where I need to store the operand. Recently, I introduced a new intrinsic that I stole from Porth, right? It's called rot. What this thing does, it rotates top three elements on the stack, right? So essentially it brings this element to the front. That's what it does. right? It brings that element to the front. And that is actually relatively convenient for our situation. And that way I can then swap yet again to bring this pointer in here, right? Like so. And now I can save the operand into that pointer. There we go. So I saved it in there. So, and now I need to save type into that pointer as well. So that means I can just do 64 yet again, and there we go. I basically, you know, saved all of these things. Like I saved type, operand, and you know, that's everything that I wanted to do. After that, I need to increment the ops count. So luckily we have a macro that allows us to do that. So essentially you push ops count onto the stack, all right, and you just do inc64, and basically increments the value to which this pointer is pointing. And there we go. We managed to implement push op. Right, that's basically how we do that. So, as you can see, it's a pretty difficult language to work with, but at the same time, it is very simple, right? So that's kind of like the trade-off. It is difficult to program in, but it's easy to implement. Since it's easy to implement, you can try to re-implement it in itself. Right, so, and we'll see if it will be possible. So far, I don't really mind to program in this kind of style. It's actually kind of fun, to be fair. It is kind of fun to program like that, trying to like visualize the stack and whatnot, and you know, also keeping track of the stack in the comments. It is extremely fun. I really recommend to try it out. Toby Prime, thank you so much for Twitch Prime subscription. Thank you, and welcome to our Epic Porth Club. So, for example, if you add a feature in the self-hosted compiler, you can use it in the next compilation of the compiler. Yes, you can. So that's actually kind of the point. So once the compiler is going to be fully self-hosted, first you will have to implement that feature, then recompile the compiler, and then you can re-implement that feature using that feature with the new version of compile. So yeah, it's going to be a very interesting process. I never done that before, and that's precisely why I want to try it, right? Because I think it's going to be interesting. Star Over, thank you so much for 6 months of tier 1 subscription. Easy. What is that supposed to mean? Thank you so much for 6 months. Would you be able to compile porth.porth in Atom? I guess. I mean, I just did, so yeah, here it is. I mean, it's not finished yet, but I can already compile it in Asm, so yeah. It is what it is. It just works, yeah, it just works already. Okay, so everything seems to be compiling, and if I try to run the entire thing, it says that compile OPs is not implemented, but that means it actually went ahead and pushed all of these things onto the stack, right? That's what it did. So let's actually check if it has all of these operations on the stack. So let's create a macro, something like a dump OPs, right? Dump OPs. And let's iterate through all of the operations on the stack. So we're gonna have a simple while loop, right, that checks where so we first probably want to push something like OPs count, all right, and we want to read the value from the OP count. And maybe first we want to duplicate this thing, right? And if this, while this thing is less, we're gonna keep like writing everything. So index, we duplicate the index, right? So we have here we have index, and I need to multiply that index by the size of the operation. So I need to do size of OP multiply size of OP. This is not how you do that. And then I want to add the ops, right? So then I do ops. And after that, I want to just read the value from this thing. And what I effectively going to be reading, in fact, is the type. So maybe we want to print only the type in here. Right, and then I just print this entire thing. So, and after I finish the loop, I'm going to just do drop. There we go. Instead of compiling the operations, let's actually simply dump the operations and see if we actually push those operations into our array. And my keyboard has died all of a sudden. I don't know why. Oh my god, something with my wire of this keyboard keeps dying for whatever reason. So I don't know, maybe I need to change the wire. Just a second. Oh yeah, finally it works. So I just had to, you know, reconnect everything. So everything seems to be okay. Okay, let's actually dump the operations. And, well, it went to an infinite loop because I never advanced the index, right? I never advanced the index. So let's actually advance the index. And as you can see here, we have 0, 0, 1, 2. Right, and here we have push int, plus, and print. And push int is 0, so we have two push ints, which is 0, 0, 1, and 2. Pretty straightforward, right? It is in fact pretty straightforward. So here we have some other things. So maybe we want to also print the operand, because why not? I think it's gonna be fine. So, but how are we gonna do that? All right, so here we just have the pointer, right? We have a pointer to the operation, so ptr. I kind of want to duplicate that thing, right? So I'm gonna duplicate it, and we're gonna have just pointer. So after I read this thing and print it, I printed the type, right? So this is the type. So, and maybe I'm gonna actually indicate that. So this is gonna be type, right? Puts. So type puts like this, and then this one is going to be operand. This one is going to be the operand, and here I do dupe, but then I'll have to add 8, right, to shift to the next field. There we go. And at the end, it probably makes sense to add some sort of like a line, right, to separate each individual operation, right? So after that, while do is not really happy with what I'm doing, probably because I want you to do something like this, right? Oh, there we go. Okay, that's pretty cool. So as you can see here, we have a type 0 operand 34, type 0 operand 35, a type 1 operand 0, because it doesn't make any sense for type 1 and type 2 operand 0, as you can see. So here we have all of these operations. So it's pretty convenient. So maybe I'm going to keep this macro for debugging purposes, right, for the future, just to know what's located in this array. So this is what you can already do in this language, which compiles to assembly, by the way. Alright, so we have an assembly of this entire thing, and this entire thing, by the way, does not even depend on anything. It doesn't even depend on libc. We're not using libc, we're working with Linux syscalls directly, right? So that's what we're doing. Okay. So the first thing we want to do, we want to be able to compile the operands, right? We want to be able to compile the OPs. Compile the OPs. How are we going to be doing all of that? This is a very interesting question. So first, we probably want to iterate them as we're doing here. Cubisus subscribed at tier 1. Thank you so much for tier 1 subscription, and welcome to our epic Porth club. All right. Okay, so here's a compile OPs, and I'm going to just iterate over this entire stuff. So 0 while dupe ops count 64 do. And this one is going to be 1 plus, and we're going to just end this entire thing. All right. So maybe I'm gonna actually just copy paste some of this stuff. So this is the beginning of the pointer, and first thing I want to do, I want to check what's the type of this thing. So here I have ptr, right? Here I have a ptr, and I'm gonna dupe this entire thing. And I'm gonna read this entire thing, which will give me a type. It will give me a type, and I want to compare that type. If this type is op push int, right, equal, I'm gonna do one thing. Oh man, this one is interesting. So yeah, we don't have anything like else if, like elif or anything like that. So you kind of forced to do a very stupid thing. Okay, so let's actually do something like to do. If this thing... So we're starting to actually see the flows of this compiler. So if it's a push int, you have to do plus, then else and... right, so this one is going to be to do, and then another one is going to be something like this. Right, so else to do. And for the last else, I think we have to do something like here, puts to do, not really to do, but it's rather unreachable, I think. Unreachable, there we go. Actually, we want to use something like eputs, right? So we have puts and eputs, which basically prints everything to the standard error, right? So this is going to be eputs, and we're going to exit with non-zero exit code. So that's basically what we're doing in here. So yeah, that's kind of a pain in the ass, and every time you add a new operation in here, it's going to become more and more painful, right? So here, by the way, maybe I'm going to do something like eputs to do compilation of OP. So this one is OP push int, right? So this is a OP push int, then plus, actually, plus print. Yeah, there we go. Walrus, thank you so much for 11 months of Twitch Prime subscription. Thank you, thank you, thank you, and welcome to our Epic Porth Club. So, yes, a compilation of push int is not implemented, right? So this is going to be a new thing. Eputs, and then we're going to exit with 1. So here we're going to have this, which is basically plus, and then we're gonna have something like this, right? Print. There we go. So, okay. Syntactically, it looks like shit, but we're not limited by indentation or anything like that. We can try to, like, at least make it look decent by using something like this, if you know what I'm talking about. Right. So, essentially... yeah, we can do something like that. So here is the first condition, and maybe we can even indent it like that. It doesn't really look that great, but yeah. So here is the first condition, then the second one. So if else, if else, if else. But the problem here is that we're having some sort of a trail of ends, right? So we're starting to have a trail of ends, which is kind of interesting. So can we do something about that? Can we do something about that? So ideally, in my opinion, we have to do something like, we need to introduce a couple of new keywords, right? Something like if, right? Then, and then elif, another condition, then and then else, and then a single and, right? Something that Python does, right? So we probably want to do it like this, and it will enable us with like long if-else chains. But re-implementing it like that probably will take some time, so I don't really want to spend that much time on today's stream on doing this thing. So maybe for now we're gonna just roll with this trail of ends, but then later I'm gonna implement elif and then. Right, I might as well actually go to somewhere like editor and add new keywords in here so we can at least see them. So we're gonna have then elif, right, I'm gonna reevaluate the buffer and I'm gonna revert this entire thing. Oh shit, okay, so now I'm gonna save this entire thing. Okay, cool. So yeah, so it will look like this with the highlighting, right? I think it's fine, right? If you want to have a chain of these like if else's, I think it looks fine. So what do you guys think? So, and it will make the language a little bit more consistent because we have a similar situation with while, right? So first comes while and then the condition, and if was kind of like, you know, inconsistent with while because if went after the condition and it looked kind of weird. Now we're forced to do it like that, and we are going to have a little bit more consistency. Right, so I think this is the first thing we want to fix in our language before parsing, because we're going to have a lot of these if-else constructions. By the way, people were constantly complaining about my huge if-else, constructions in here, right? The reason why I wrote the code like that is because I expected that I'm gonna translate this code to Porth. Right. I expect that I'm gonna translate this code to Porth. And the reason why I use this if-elses is because on the language level, they're extremely simple and extremely easy to implement. Right. If I can get the job done by using such a dumb and simple construction, I could be able to implement the Porth itself. Does it make sense? So I intentionally actually used this kind of stuff. I intentionally tried to avoid any hash tables, because if I used hash table, I have to implement it in a language. Right. So when you're implementing a language in itself, you always pay for the convenience. You want something convenient as a dictionary, you will have to implement a dictionary from scratch. If you can get away without a dictionary, you don't have to implement it, right? So makes sense. And that's precisely why I did it like that. So I tried to keep the code of the Python implementation as dumb as possible, because I knew that I'm going to be re-implementing it in a dumb language. You see? You see what I'm talking about? And it was kind of hard to actually keep doing that while everyone is screaming, no, compress that in a dictionary, no, use that feature. No, it is intentional. It is actually intentional. So the code is intentionally dumb because it was planned to be re-implemented in a dumb language. See? All right. So if do sounds nicer than if then, what's do is going to do? So you mean instead of using then, just use do, right? Just on a syntactical level. I'll think about that. I think it's actually a pretty cool idea. It will actually allow us to syntactically transition from if to while loop, right? So you have if do, right? So, and then you realize that you want to perform the body several times while the condition is true. For you, it is super easy to just swap if to while. Maybe, I'll think about that. Thank you. I think it's not a bad idea. Anyways, for now, we're gonna just have this trail of, ends. So first end closes this thing, so you have to put as many ends as you have else's, I suppose. So I'm gonna put it to do. Introduce a better construction to avoid this madness. There we go. So we're gonna have a first to do. So as you can see, we're already getting somewhere. So the language is powerful enough that you can do some things, and this is actually super cool. I'm really excited. Okay, so let me take a look. So this is the compilation. While do is doing some weird ass shit. Okay, so here we have a type operation, right, and I duplicated it, and I suppose the problem in here is that I probably want to drop it, right, so I'm supposed to handle it properly. So if I drop it in here, there we go, it is compiling, and it's already failing. Compilation of this thing is not implemented yet. So as you can see, compilation of push int is not implemented. So how do you even implement push int? This is a very interesting question. So let's take a look at the compile file, and I think it's somewhere yeah, there we go, generate. So push int. So yep, we're already translating Python code to Porth. Look at that, we're already doing actual thing, chat. Isn't that cool? I think it's pretty fucking cool. So how are we going to be doing that? So for now, we're going to be actually printing all of that on the standard output, right? So this is going to be something like, I can literally just grab this string, right? So this is going to be puts, then the next one is going to be puts, and this one is going to be rex. There we go, puts. Cool. So of course, we don't have a way to print the numbers yet. We're going to introduce that way a little bit later. So I have a little bit of a trick up my sleeve. So you'll see. Okay, so as you can see, it's already tries to compile two numbers, right? It already tries to compile two numbers. So, and if you add more numbers in here, right, something like 420, it will compile more numbers. Our self-hosted compiler already generating assembly. So we're not even 1 hour into the stream and we're already fucking generating assembly in Porth. Isn't that fucking exciting? My god. So it is capable of doing things. So of course it's not compilable by NASM, but I mean it's generating a sequence of characters that is close to something that could be compiled by NASM, which is better than nothing, right? So we're all like slowly getting closer and closer to actually compilable code. Okay, so let's actually implement plus, right? So of course this one is not going to compile, so I'm not sure if I want to put it to do in here. I'm going to go back to that a little bit later. So plus, let me find plus. So here is the plus operation. Plus operation is actually easier to implement because you don't even require any parameters, right? So it just doesn't matter. Let's actually do it like this, I suppose. Yeah, let's just remove that. And then I'm gonna do a put. There we go. There we go. So yeah, we managed to do 3 numbers and a plus operation. How about that? So, and the last thing we need to do the print, and the print is rather interesting because print jumps to a hard-coded instruction, right? So as you can see, it calls to print, and this is instruction that we wrote directly in assembly. So we'll have to maybe copy-paste this entire thing up front. Yeah, let's actually go ahead and copy-paste this entire sort of header up front and put it like right in front of this thing. Right, so I think we're actually getting somewhere, chat. How about that? So just a second. So I'm thinking I'm gonna be using a little bit of a Emacs magic, just a tiny bit, not too much. A boom, boom, puts. There we go. So yeah, we're pushing this thing. We're printing this thing while generating this entire shit. Okay, so as you can see, we're already generating something that could be potentially compiled by NASM at some point. Okay, so, and if we want to implement the print, all right, so this is going to be print. This is what we're going to be doing. All right. All right, and as you can see, we generated the full program. But on top of full program, we also have some sort of like not really header, like a footer, right? So we have a header of the program and also have a footer of the program. So let's go ahead and also copy paste the footer. So we do a bunch of stuff in the footer, as far as I can tell, especially when it comes to the especially when it comes to the strings, but I think we're not gonna do anything. So I'm gonna do exit syscall right at the end of this generation. Just an exit syscall. So this is gonna be like that, and I think we're almost ready to rock and roll. So this is gonna be puts. So this is one thing. We don't need a data segment yet. A data segment is only used for the strings. We don't support strings yet, but we also need to put the BSS memory, right? So we need to introduce, oh, the memory capacity. So this one is going to be rather interesting. Okay, so I'm going to just do puts, and memory capacity is going to be implemented later. Okay, so what do we have in here? Yep, I think this does in fact generate something that we can then later try to compile. You really need a formatter to align all of those inputs. Do I really need it? I mean, is that what you want? I mean, it's not that hard. It's just like I'm not sure if it's needed. Is that what you want? Is that what you want? Okay. So now, what do we have? Right. So maybe I'm gonna actually put a to-do in here. To do in here and to use a better construction to avoid this madness. Alright, how are we going to be printing the numbers? Well, we have already an instruction that prints numbers, right? So it's called something like this, print. But the problem with print is that it's more of a debug instruction, right? It's a debug instruction, and one of the things it does, it actually puts a new line at the end of the output. Right. Recently, I implemented a function in Porth that is capable of printing numbers, right? And it's not hard-coded. So I would like to actually bring it. I think it's somewhere in examples. I think I already implemented it in Porth. Yeah. So it's called putD, right? So puts prints a string, right? It prints a string, but putD is capable of printing numbers, right? Unfortunately, it needs a special buffer, right? And you have to allocate that buffer manually in the mem. And that's why I couldn't put it into the standard library, because we have no way for a standard library to just say, okay, reserve me some memory in mem. Unfortunately, we don't have a way to do that. And this is because the language is very dumb and very simple, right? And adding feature like that would actually complicate it, and I don't want to do it right now. Alright, so putD buffer. So where are we gonna allocate putD buffer? First of all, you only need 32 characters for printing numbers, right? If you take a look at, let's say, 2 to the power 64, right? So if you go to 2 to the power of 64, so this is the maximum number that you can have in 64 bits, right? And if you convert it to a string, here is the number, and if you take the length of this entire thing, the length is going to be 20, right? So you need a buffer that can accommodate 20 characters, and to align properly with like a power of 2, I usually allocate 32 bytes, right? So, you know, you have extra padding, and it also aligns on 64-bit architecture quite nicely, because if you divide 32 by 8, right, you get 4 64-bit numbers, right? I think it's actually pretty good way of, you know, pretty good size, I would say, pretty good size. Okay, so let's put this thing in here, and where do we allocate everything? So I'm gonna put the buffer somewhere in here, right? I'm gonna put it somewhere in here, and I'm gonna allocate OP's count after putD buffer, and the size of putD buffer is gonna be 8 characters, right? There we go. So as you can see, we have to like manage the layout of memory manually. It is inconvenient, but at the same time, we don't have to. It's super easy to implement. Okay, so and let's go ahead and copy paste this macro and see if we can use this macro, right? So this macro should allow us to print some shit. For instance, in Porth, we have a memory capacity, right? So we have a memory capacity which is 640 kilobytes because it's enough for everyone. Right, it is enough for everyone, so let's actually make this thing here as well. So this is a memory capacity, 640, like so. So why does OP dash have an OP count have a dash and everything else an underscore? There is no particular reason. This is because you can use both dashes and underscores in the names. So it's more of a like whatever. So it just happens to be there. Maybe I'll have to go through the entire thing and make a consistent style, but I just don't care. It's just like it's the same level of question, why spaces and not tabs. Like, I don't care. I'm trying to solve a more complicated problem right now. Okay, so here's the memory capacity that we have to put in here. And so what I'm gonna do, right? So I can now do the following thing. Puts, right, then memory capacity, put D. There we go. So, and this is how we format the entire thing, right? This is how we format the entire thing. And of course, I forgot to actually switch to compilation mode. Boom, 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 and unknown word put D buffer. Okay, so I can just do it like that. Another put D buffer. There we go. So as you can see, it generated the number properly. Now we have to use this thing in here. So the question is, how are we going to be using all of that? Well, here's the push int, right? Here's the push int. So in here at the top, we have a pointer, right? So here is the pointer, and essentially, I have to do something like this, right? So this one is going to be put s, and then I have to put a pointer. So I want to duplicate this pointer, right? So this pointer will become duplicated, and I need to offset that pointer by 8, right? So now it points at an operand, right? We're pointing at an operand, and we're reading that operand from here, right? We're reading that operand from here. And then I'm printing it as a number, right? There we go. So, and I want to repeat the same thing here as well, right? So this one is going to be puts, so, and it's just like this. We're just reading it twice. Cool. That should be it. So now we are, in fact, should be generating a correct code that pushes the numbers into the stack, and something went horribly wrong, and I don't really know what. That's really strange. So I don't really know what happened. Why did it start failing? So it started to fail somewhere. So it pushes 0, it keeps pushing 0, and it doesn't advance for whatever reason. I don't really know why. Like, what the hell has happened? Okay, so I can try to just comment out this entire thing and just do puts, and see. Yeah, okay, so there's something in this code that fucks it up, and I'm not really sure what exactly fucks it up in there. Right, so puts should not return anything, right? Puts shouldn't return anything. Then we do dupe, right, and then we add 8, then we read it, and then we try to print it as a number, right? So what is actually going on in here? So if I try to do something like print, will that work instead? Yes, and if I do put D, it goes indefinitely for whatever reason, right? So it fucks it up on the level of put D. This is really strange, so something wrong in here. Something really wrong in there. Alright, so if I do print, right, well, what it will print? It will print it incorrectly. It does print the correct numbers though, right? So it prints 34, 35, 420, but it prints it with like a new lines. So maybe this is because I changed some of these things in here, like underscores and whatnot. Put debuffer, 8 plus, ops count. Oh yeah, I know. Is that because size of OP? Is the size of the put buffer correct? It is in fact correct. It is not. Thank you so much. Put debuffer cap. Yes. Thank you. Yes. So now it is working. Well, I mean, I didn't test it yet. Just a second. So this is going to be put D. There we go. So now it is working. Yeah, finally. Thank you so much. Thank you, thank you, thank you. So as you can see now, we're generating the correct thing, hopefully. And the output of this entire stuff should be compilable, if I understand correctly. So let's actually go ahead and remove 420, right? So let's just go ahead and remove 420 and output this thing to, I don't know, hello.asm, right? So hello.asm generated this stuff. Oh my god, okay. So it also printed, maybe we should print that to standard output at some point, but yeah, I think I'm gonna do the following thing. I'm gonna just run Porth, and there we go. We should have a hello. And after that, I should be able to compile the hello asm to hello o, right? And then I can do something like ldo hello, hello.o, and really incompatible. Wait, what? How did I compile this entire thing? F64, I forgot to say F64. And then I'm linking it into the finals Gitable, and as you can see, this thing printed 69, right? So our hard-coded program pushed 34 and 35 on the stack, right? 34 and 35 on the stack, then it summed it up, and then it printed it. So that's pretty cool. So we don't really have a way to read files in this compiler yet, but we can hard code intermediate representation of a program with the limited amount of instructions and generate assembly of the programs that do those things. So you basically can hard code the simple Porth program in here. Right, so it's a hard-coded program in here. So we can do more different things, for instance. So this is one program, right? So macro program 69, right? So we can put it like that, and then I can just put it like this. So program, it's not 64, it's 69. So program 69, and then I can have another program, for instance, op push int 1. Push operation, and then I can instantly print it, right? And I can just do something like 1, 2, 3, right? And then I end macro. Macro 1 to 3, program 1 to 3, program 1 to 3. And if I swap it out to program 1 to 3, it will generate a different program now, right? So I can already hardcode things. So the only thing that is left in here is essentially to wire up, like implement the process of reading from the file and filling up the array of OPs, right? And I can already have like swap out different programs and stuff like that. Unfortunately, this entire thing doesn't run external programs like, you know, NASM and the linker and stuff like that. And this is something that we'll have to implement at some point. And it would be really interesting to implement because one of the things we'll have to do is to run exec-v or exec syscall, and this syscall is actually rather complicated. So Linux syscall table, right? Let's take a look at Linux syscall table in the Chromium OS. So I think something like exec, right? So where is the exec syscall? Exec-ve, right? So this is the syscall that we'll have to probably run, and it accepts the pointer to the file that you want to run, then the pointer to the arguments, the environment, and all of that has to be prepared in the memory, right? So we'd have to lay out all of these strings in the memory and then pass them to exec-ve and stuff like that. And yeah, doing fork is going to be super easy because fork doesn't even accept any arguments, so it's super freaking easy. But exec-ve requires preparing all of that stuff, and it's just like, we'll see how we can do that. So yeah, we'll see. I think it's going to be interesting. Though for NASM, right, you can hard code a lot of things. I think you'll be able to hardcode all these things. We'll see, we'll see. The winner gets a T, that's for sure. So simulation is not implemented. So let's go to compile ops and add a couple of to-dos, right? So Porth does not run NASM NLD as external commands to finish off the process of compilation, right? So I'm gonna leave it as a separate to-do. And then I think we can focus on something like a simulation, right? Simulation will let us like simulate things quite easily, right, without, you know, trying to compile this thing, because with the compilation problem is that you have to save the output, then compile it manually, then link it manually, and until we implemented this to do, compilation mode is going to be kind of useless. You know what I'm talking about? So you really need this convenience feature, like you need compiler to run all these external tools for you, otherwise you're going to have a really bad time. So, and until we have that, I think we want to implement a simulation mode, because simulation is going to just go through the entire thing and interpret that thing, right? So that makes sense to me. Yep. And how are we going to be interpreting this entire thing? Well, we literally are going to interpret those things, right? So I think we need to allocate some memory for the stack, right? So we're going to be simulating the Porth stack in Porth, right? So we're going to pre-allocate some memory for that stack. And the question is, what's going to be the stack limit? I don't know, we'll see. So let me think. So I'm going to call it sim stack capacity. And I'm going to allocate, let's say it is going to be 1024, right? So 1024. Also, we have to keep in mind that 1024 multiplied by 8, because a single word is going to be this. So I think it's going to fit into our memory limitation. Okay, so it's simulation stack capacity. So where I'm going to put all of that, that's a good question. So here we have a put debuffer, and I think I'm going to put it somewhere here. So sim stack count. Right, and sim stack count is going to be probably located after put debuffer, and ops count is going to be located a little bit later. Okay, so sim stack count after this thing, then sim stack is going to be located after sim stack count, the size of which is 8 bytes, right? And the ops count is located after sim stack, the size of which is sim stack capacity multiplied by 8, 8 multiplied and plus. So yeah, there we go. Right, so in the memory we have first the buffer for the put D operation, then the simulation stack counter, then simulation stack itself, which is limited, and then we have operation counter, how many operations we have in there, and the array operation until the end. So yeah, that's basically the layout of the memory. So memory layout. So this is a memory layout. We're gonna keep all of that in a single place. So you see, you kind of have to like chain them together. It's not particularly convenient, but you can get used to that. So didn't I send Discord notification? Oh shit! Fuck. I'm so sorry. Alright, let's actually send the Discord notification. I'm really sorry about that. Fuck. This doesn't make any sense. Alright. Live on Twitch. God damn. Okay. So, rewriting my language in itself today. HTTPS. Okay. Sorry for the late notification. KW. I'm already streaming for 1 hour. Okay. Yep. I'm very sorry. So yeah. Isn't that cool? I think it's pretty cool. Shit. All right. So didn't I make any mistakes? Okay, everything seems to be all right. Put D, stack counter, then that, and everything seems to be okay. So now we have a stack. Cool. And maybe we also want to have some operations for the stack, right? So we want to have a macro, sim stack push, right? Which pushes whatever value you want on the stack, right? This one is going to be eputs. To do sim stack push is not implemented yet. All right, so this one is going to be eputs, and we're going to exit with one. And another one is going to be sim stack pop, right? And we're going to do it like that. So this is going to be pop, and we're going to end this entire thing. There we go. So we definitely need these two operations to, to work on the simulation stack. Yep, and I think that should be enough to do all of these things. We'll see how it goes. So let me see if I didn't break anything. So here we're compiling this entire stuff, and if I try to run it, everything still runs. So the thing I wanted to check, if after introducing like a new stuff in the memory, does it break anything? So hopefully it doesn't break anything. So everything seems to be fine. Right, so now I'm gonna go back to the compile and replace it with a simulation, right? Simulate ops, right? Simulate ops. And if I try to run this entire thing, as you can see, simulate ops is not implemented. So what we're gonna do in here, we're gonna do pretty much the same thing. I might as well even copy paste this loop to save myself some time, right? Because we're literally going to have the same loop. The only difference in here is going to be that when I need to push int, I'm going to be pushing it into the simulated stack, right? So I have to do something like, well, I might as well just grab the operand, right? So here is the operand, and I'm going to sim stack push. There we go. So I just pushed it into the simulation stack. Yep. So then what I need to do, I need to read two numbers from the top of the stack and sum them up and push them back. So in here, I think I would presume that sim stack pop just pops the value from the stack, right? So it adds the value into your stack. Then you do another one and you have B. Then you do plus and you push it back. That's it, actually, believe it or not. So, and if you need to print this entire thing, well, we need to pop this thing and we're going to print, because in the Porth itself, we already have a print instruction. So we're using print instruction of Porth to simulate print instruction of Porth. Just think about that. So we're already using the print instruction of Porth. So simulating language in itself is super easy because we already have all of the operations we need to simulate. So that's why it's so fucking easy. So that's the entire simulation. So, yep, nothing much to say. It's just like, that's what it is. Pretty cool, huh? So let's see what's gonna happen. Well, it's not gonna work yet because we don't have sim stack pop and sim stack push. So, and let's take a look. So both branches, blah, blah, blah. So I suppose we need to do some of these things. So stack pop is supposed to return something. Let's actually return like 69 or whatever. And in here, this thing accepts one number that we have to drop. Okay, so now this thing will compile and stack push doesn't work anymore. Okay, that's pretty cool. You still have to implement print somewhere. It is implemented in here. Here it is. Here is the print implementation. So for the person who said you have to implement print somewhere, here it is. So yeah, it is what it is, and it isn't what it isn't. Okay. Alrighty. So Stack push. I suppose first thing I want to do, I want to actually check if we don't overflow the stack, right? So I think it's quite important. So I'm going to take sim stack count, and I'm going to try to read this entire thing. And if this entire thing is greater or equal than the stack capacity, so we're going to have sim stack capacity is greater or equal, that means we're going to complain about this thing, right? So we're going to say something like here, it puts error data stack stack overflow in simulation mode, it puts and one exit. There we go. So it's pretty convenient for reporting errors. So after that, what we want to do, we know that we have a value on the stack, right? We have a value on the stack. So now we need to take the pointer, right? Somehow I'm gonna push the sim stack, right? So here is the sim stack. Sim stack is on the pointer. Then I push the sim stack count, and I have that on the pointer. I need to read this entire thing, so that means I just dereferenced it. So then I need to multiply it by the size of the word, right? So this is going to be something like this. I multiplied it, and then I have to add it back to the stack, and then I'm gonna use the write operation to write all of that back to the stack. Okay, so after that, what I have to do, I have to just increment the sim stack count, and there we go. I think I implemented this entire thing. That was freaking easy. Okay, so cool. That was easier than expected. So if I try to compile this entire thing, now it complains that sim stack pop is not implemented. Okay, so let's do a similar check. Sim stack count at 64. I think we want to check that it's not equal to 0. So if it's equal to 0, right, 0 equal, we're going to say that it's a stack underflow, right? So you're trying to pop from an empty stack, and this is something that you shouldn't do. Right, data stack underflow in simulation mode. All right, and the first thing we probably want to do is to decrement the stack counter, right? So we want to do something like dec64. And then we want to read whatever we have on the top of the stack. So this is going to be simulation stack count. Then we read that thing, multiply by 8, and we read that entire thing yet again, and there we go. So this is how we're going to pop from the stack. I think I'm getting the gist of this language, so because this kind of stuff becomes really easy to implement, right? So it's just like, yeah, that's how we do that. So I think it's not going to compile because we don't have dec64. But I think we can quite easily implement it in a standard library because inc64 is located in a standard library, so we can just implement it there. I'm sorry if it was too loud. I'm just banging my my table. I didn't mean to do that. Right, so what do we have in here? Yeah, unknown word dec64. Okay, so let's actually go to std. Where do we have inc64? So here is inc64, and I suppose dec64 is going to be literally the same, except instead of plus, we're going to be using minus, right? So, yep, that's the entire thing. Nothing much to say, right? Okay, so, and invalid argument for load 64. Really? Why do you... Oh, this is because I have to cast this entire thing to the pointer, right? So I have to cast it to the pointer, both of the branches. So stack pop. When I... Okay, so this one is rather strange, because I wouldn't say that... expanded from the simulate OPs. So we have unhandled data somewhere, and I'm not really sure where. Is that in a push? It feels like it's somewhere in a push, but I'm not 100% sure. Well, I would expect this thing to be handled like this, but I'm not really sure. What's the difference between a load 64 and force load 64? Okay, this is actually a very good question, Bolos. Thank you so much. I forgot to mention that, I think. I don't remember if I mentioned that. Okay, so at some point of the design of the Porth, I introduced store operation, right? I introduced store operation, and essentially how I chose the order of the argument for the store. I decided that first argument is going to be the pointer, and the second one is going to be the value, right? So if you have this thing on the stack, then you perform the store, it will save a value at that specific pointer. Then later, I discovered that the fourth store operation actually takes the arguments in a different order, right? So, and I thought, should I change it? I'm not sure if I should change it because I kind of like this order, because that order allows me to do the following thing where I can just use mem, right? So I push the pointer to some memory, then I push value 1, and I just store that value there. Then I can just do, actually I can do it like that. So I duplicate it, value, store it. Then 1 plus, and again, duplicate it, store it. So it allows me to chain these kind of operations, right? If the order of the arguments was swapped, I won't be able to do that. Right. So, and for quite some time, I've been using this order and I was happy with that. And then I realized that there's quite a few situations when I would like to prefer this order. So, and I was thinking, maybe there is a reason for this specific order, because usually when you program in stack-based language, you want the pointer to be here. So I decided to run an experiment. Why don't I support both of them? So I have both operations, my original store with pointer and value, and the fourth tile with the value and pointer. And as I program, I want to see which one is more convenient to use, and that's the one that is going to be left in the future. So at some point, we're going to remove one of the operations. Does it make sense? So it's sort of like a running experiment. So basically, my style of the operations is dot, comma. The Porth style, I think, at bang, right? And they just basically use different style of arguments. But for I think it's the other way around, right? For reading, it doesn't really matter because reading accepts one pointer. But for this, for the sake of consistency, I decided to introduce it anyway, right? So it's just like, yeah, whatever. So does it make sense? It's kind of a weird reasoning, but yeah. All right, so something doesn't work. I'm not quite sure what. Something doesn't want to compile. Let me see. So some of the branches don't properly work. So and I wonder which one. So if I basically go ahead and just comment out all of these things, and I just run it like that, everything seems to be working. So if I enable this thing, it works. If I enable this thing, okay, so there is a problem with the stack pop, right? Stack pop is not implemented correctly. All right, that is really, really weird. So expect stack pop to return something. So here is the count. All right, then I decrement this count. Stack pointer, then that thing, then I read that thing. I multiply it by 8, and I forgot to add it. Okay, so then I'm casting that thing. Maybe the casting that stuff is not really needed, but I think, yeah. Okay, so sim stack pop. All right. So where is my simulation? Simulation 2. So I should be able to do something like that now. Cool. All right. So now we are about to run the simulation. And as you can see, this is what we have in the simulation. 1, 2, 3. And this is precisely the program that we coded in here. We can swap it out to program 69, which actually pushes 34, 35 onto the stack, sums it up and prints it. So this entire thing is going to print 69. There we go. We're simulating Porth, more of a like internal representation of Porth in itself. That's what we're doing. Isn't that cool? Isn't that cool? I think it's pretty fucking cool, mate. I think it's pretty goddamn freaking cool. Alrighty. So yeah, we have compilation mode, we have simulation mode. The only thing that is missing is actually accepting an input file and parsing it and filling up these operations from the input file. Right, so this is one of the things that are missing. And I think I'm going to create a separate to-do for that. Right, so this is going to be a to-do. Parsing file is not implemented. So basically we just need to have a procedure that goes over the string and just uses push OP, like to push operations in there, and then we can either call to simulate ops or compile ops. Right, so, and that's basically what we need to implement in here. It's just like, yeah, that's what we need to do. So, and this is basically the base of the self-hosted compiler. It's like a skeleton that we just have to keep extending and extending until we implemented the whole compiler, and then we can try to recompile the compiler in itself, right? So, yes. So another thing that is missing, okay. User cannot choose the mode com versus sim from the command line args. You know how in Porth you can actually specify, in Porth Py, you can specify the subcommand, simulation or compilation. We don't have that yet, though it is relatively easy to implement, I think. I think it is relatively easy to implement, right? Because we only need to take a look at the first argument and just see if it was provided or not. But yeah. So the first thing I want to do, by the way, is essentially commit whatever we have already, right? Let's actually go ahead and commit whatever we have. So hello is not needed. So add dex64 to std porth. Right, there we go. So porth mode, okay, add then and elif keywords to the Emacs mode. We might as well actually add them to Vim mode as well, right? So for those who's following this entire stuff, we have a folder called editor, and we have support for two editors, Emacs and Vim, and I'm supporting like two of them. Vim script. Do I have a highlighting for Vim script? I'm not sure if I have it. Okay, so editor, Porth, Vim, and where do we have this stuff? Okay, so here's else and elif, and another one is going to be then. So I'm going to add these things in here. Okay. Add then and elif keywords to the Vim plugin or whatever, right? So I want to git ignore the executable of Porth, right? So it's going to be Porth. Okay, so initial implementation of Porth compiler in itself, right? So I'm going to push that right into the repo, I suppose. So this is going to be in a separate branch. Though I'm not sure if I want to do a separate branch in here or pull requests, because we don't have anything on CI that can test this self-hosted compiler yet. I'm gonna do that a little bit later. So maybe I'm gonna just go ahead and merge self-hosting, and I'm gonna push directly into the master, because right now we're just experimenting, right? So there's no reason to have separate branches. So I think it's gonna be fine. All right. So here's the Porth, and you can check out the this thing in the repo. You can find the repo in the description right here, or if you're watching live, you can find the repo in here. Right, so if you go to the repo, you will find the compiler, Porth compiler in here. So here it is. This is what we implemented on today's stream. I'm actually surprised, like the code is kind of like resembling whatever we have in Python, and that was actually my goal, right? I want you to write the compiler in Python so it's easy to translate it to Porth, right? But I already mentioned that, right? I already mentioned that. Okay, so maybe we're gonna implement like a last feature for today. Basically subcommands, right? I think it should be relatively easy to implement subcommands because you just have to grab the command line argument, and that's basically it. You just grab the command line argument. Let me see. So we can do argc, right? Maybe we're gonna do it somewhere here. So I'm also thinking I'm gonna introduce like a macro main, and it's gonna be sort of like a entry point of the compiler, and this is where we're gonna start doing things. So here we first push the program, we prepare the program, and then we either simulate the program or do something else, right? Okay. I take the command line arguments. So argc intrinsic pushes the amount of command line arguments onto the stack. So if we have less than 2 command line arguments, we need to print an error. First of all, we probably want to print the usage, right? So we want to print the usage, and then I want to print an error that goes like this. Error, subcommand is not provided, right? Subcommand is not provided, e-puts, and then we exit with non-exit 0 code. And then we're going to have something like usage. And let me take a look at the usage in porth.py, right? So this is going to be the usage. So for now, I'm not really sure if we're going to have options or the arguments. I guess so far we're going to have only, subcommand, right? We only have subcommands. So this is going to be puts, maybe even e-puts, right? So this is going to be a new line. And the subcommands that we're going to have, subcommands, is going to be compilation, right? So this is the compilation subcommand and the simulation subcommand, right? So this is the first one, actually comes the simulation, right? We live in a simulation, so simulate the program, and this one is going to be compile the program. So this is what we're going to be supporting so far. Later, as we support more things, we're going to be extending this usage thingy. Okay, there we go. So if I try to now run the Porth, it will complain. As you can see, it is complaining. Subcommand is not provided, right? If we provide the subcommand, it will interpret it, but it doesn't choose between compilation and simulation, right? So I think somewhere in the standard library, we do have a way to take nth command line argument. So we literally have nth argv, and that will give us the string, right? So we can do something like 1, and that gives us an null-terminated string, right? That gives us null-terminated string, but that is not enough because we need to be able to compare this thing with something, right? So we could implement something like strcmp, but strcmp is actually kind of overkill for what we're trying to do, because strcmp also checks, like compares it in lexicographical order, right? So it's just doing lexicographical order. I hope I pronounced it correctly, but we don't really need to do that. The only thing we need to check is whether one string is equal to another. And that is easier than doing strcmp, because in strcmp you have to return -1, 0, or 1, depending on which string is bigger or smaller. Whether if, like, rather than that, we could have implemented str equal, which returns either true or false, depending on whether the string is equal to something, right? So I'd rather actually try to implement something like this, str equal, right? So, and if this is a compilation, right, we're going to do the following thing. So we're going to push the program, and we're going to simulate the program, right? Might as well actually pre-push the program before doing anything else, right? Somewhere here. And then we can simulate it, right? Something like this. Then else, we have to take it it once. Well, we might as well actually just take this thing once, duplicate it. Oh, and by the way, so the thing that we get from nth arg is actually null terminated. So that means str equal should work on null terminated strings as well, which means that this thing also have to be null terminated. Okay, so I think that's quite important to remember. So this thing is a simulation, right? So it will try to simulate this thing. Otherwise, if you do compilation, it's supposed to compile those things. Otherwise, we have to report an error, something like here, he puts, maybe not really that, but we can try the following thing. Error. Maybe we can, yeah, we can do a usage, then error, unknown subcommand, this, he puts. So we have that unknown subcommand on this stack, so I have to do dupe, then strlen. Maybe I have to duplicate it twice because this will kind of underflow this entire stuff, and we're not allowed to underflow that. So I'll have to do it like dupe, I suppose. I'm a little bit tired already. So I think I'm gonna do it like that. So unknown subcommand, he puts, and then one exit, and this is gonna be end, and this is gonna be end. There we go. Cool. Let's go ahead and try to compile that. Doesn't the string literal? Oh yeah, it does give me the string literal that I have to drop. So we have to do something like swap drop, right? Swap drop. Yeah, thank you so much for mentioning that. So maybe we need to have some, you know, null terminated string literals for these kind of situations. Consider adding null terminated string literals. Right, because I think for this kind of situations it's going to be super useful. Consider any null terminated string literals, maybe something like dot, and basically what it will do, it will automatically add null terminator at the end of the string and not push its size. I think it's actually kind of interesting idea because we're going to be interacting with the C code a lot. And the C code wants to have null terminated things. Well, we're not even like using C library. We're just calling to kernel. And kernel already expects null terminated string for us. So there's literally no way we can escape null terminated strings unless we write our own operating system, right? You see? So it doesn't matter how much you want to escape null terminated strings, like you won't be able to escape them on neither of the existing operating systems. Because all of the modern operating systems in the syscalls, they do expect null terminated strings. So it's just like, there's nothing much you can do. But yeah, for now we're gonna do that. I'm not really sure about the specific syntax for null terminated strings, but we'll see how it goes. All right. So let's see if this entire thing compiles. So it's actually like pretty big, not gonna lie. So 225 lines of code. Okay, so we don't have a streq, so we have to implement this thing, right? streq. Okay, so how are we gonna be doing all of that? This is a good question. So to do inputs. streq is not implemented yet. Exit. There we go. Okay, invalid argument. And of course, this entire thing has to return like true or false, right? Both branches. Okay, so this one does something bad with it. So compile ops. So let's compile ops. So maybe I want to do something like this. Okay, both branches. I'm not really sure. Like, who puts something on the stack? Is that the usage that puts something on the stack? I'm not quite sure. Somebody is doing something with the stack. So, yep. Not sure. What does it say? So I guess we have something unhandled. Nth arg. Man, I'm not sure. Okay, so let me see. Alright, that makes sense if I push this thing. Okay, unhandled data on the stack. I suppose what we have to do here, we have to don't forget to drop that data. Right, and then, yeah, so that's what we're doing here. And I'm actually confused. Oh, strq has to accept. Okay, so what we have to do in here, we have to do drop. I see. Yeah, there we go. So that makes sense. Yeah, there we go. So that is perfect. That is perfect. So now I can enable this into stuff. It's actually pretty useful. These kind of checks are super useful because otherwise it would fail at runtime. Okay, so now everything is working. Cool. So we just need to implement strEq, and in here, what do? We just have 2 pointers, s1 and s2, right? So should be relatively easy to implement all of that, right? I think should be relatively easy. So while so s, right, we have to take maybe I'm just thinking how we're gonna be approaching all of that. I'm gonna do over, right? So this will give me s1. Then I'm going to dereference this entire thing. Well, I mean, I have to dereference it as 1 byte. That will dereference this entire stuff. And then this thing shouldn't be equal to 0. So this thing is not equal to 0, right? Then I'm going to do another over, right? So that will give me that. I will dereference this thing. I'll dereference this thing. And this thing should also not be equal to 0, right? I'm gonna put and between them. Right, I'm gonna put and between them. There we go. And while this is true, we're gonna be essentially incrementing. And maybe there should be another thing, I suppose. I think maybe should be another thing. We should check that the characters that this thing point to are equal as well, right? But we have to somehow get rid of this thing from the while loop. Luckily, our language is concatenative, which enables us to do a pretty interesting thing. We can put ifs inside of while condition. You see what I'm doing? Right, if this thing is true, right, it will remove it from the stack, allowing us to actually perform even more checks in here. Right, so, and we can put false somewhere in the else, right? So, yeah, essentially it's like using like ternary operator inside of the while loop, but I mean, we don't have a break. We could have used something like break, but we don't have a break. So, we have to use something like this. Right, so, and in here what I'll be able to do, I'll be able to do over dot yet again, so it's going to be s1, then over dot, which is going to be s2, and then I can check if they're equal, right? So There we go. So if we go to that branch, this thing will be checked by do, otherwise it will be checked by do and it will fall. So this is how we can basically stop the loop without having a break, right? We can move the if condition inside of the while condition. So that's basically what we can do in here. And in the loop itself, we're going to be just incrementing the pointers themselves, right? So, and essentially, so I need to increment S2, right? So this is going to be 1 plus, this one's going to be plus 1. Then I suppose I need to do swap, 1 plus swap, and that will increment you know, this thing. So there we go. So there we go. There we go, there we go. And after that, I need to check whether they're equal or not. To check whether they're equal or not, right. So I suppose what we'll have to do, right, what we have to do is, so at the end of this entire thing is going to be S1 and S2, right? So we have S1 and S2. So they should point both at 0, right? We should point both at 0. So essentially what I want to do is yes, I want to do something like this. Equal. All of them have to be equal. Both of them have to be equal to 0. If some of them are not equal to 0, well, that's very bad. Interestingly, oh yeah, that's fine. Okay, so that means the return is going to be here, right? And what we need to do now, we need to get rid of these two things from the stack. So we're going to do swap, swap, and then drop. And we're going to do that twice to get rid of this thing completely. All right, so this is roughly how I wanted to do that. And let's actually go one more time through the entire thing to see if, you know, if everything's okay. So over read 0, 0 not equal. Or read 0 not equal. And, right, then it's consumed by if. Right, and if it's not true, it's going to be false, it's going to fall over. If it's true, we're going to do S1, this, S2, this, equal. If they're equal, what we're doing is essentially plus 1, then we need to swap this thing, plus 1, and we have to swap it back. Right, we have to swap it back. Okay, so after that, after we're done, we're gonna have two pointers here. So what I do is S1 reference equals 0, S2 equals 0, and I have this thing. And to be fair, maybe I can actually simplify this entire thing to get rid of this swap and drop. Right? Can I simplify this entire thing? S1, S2, I can probably just go ahead and dereference this thing, right, like so. 0 equal, right, so I can do that right away, equal to 0. Then I can swap this entire thing, 0 equal, and so basically I'm consuming right away. So, and it doesn't really matter in which order we're doing this thing. Oh, this is actually very interesting. So that probably means we don't even need this second swap. Right, we don't really need that because it doesn't matter in which order. So we can just keep swapping them around and just like it doesn't matter. Yeah, it's actually pretty cool. Okay, so we're gonna keep it like that. Okay, so that could be the implementation of str equal, hopefully. Does it make sense? I think it makes sense. Okay. All right. So, and wait, did it? Oh shit! Wait a second. Okay, I didn't provide anything. I provide sim. It simulated the thing. I provide com. It compiled the thing. We have subcommands. What the fuck? That was easy. Alright, so there you go. If you want to simulate, you do sim. If you want to compile, you do that. So look at the simulation, like how much time the simulation takes. It's actually super fast. The simulation of summing up 34 and 35 takes 0 milliseconds. So that's how fast it is. Alright, in Porth. I can actually swap it out now. This is actually super cool. So Porth, and in here, let's actually swap out the program. So the program was 69, right? So let's do program 1 to 3. Right, let's recompile the entire thing. Let's recompile the compiler, and if we simulate it, now it's a different program, right? So now I can do Porth, simulate, and it just does that. That's pretty fucking cool. My god. So user cannot choose the mode compilation. So now the user can choose the mode. So you see how powerful this language is, right? So you can actually parse command line arguments, and you can choose between different things. Like it's actually like a useful language. Look at that. Look at that. I think it's actually pretty cool. Right, and we're gonna make this compiler more and more powerful, and eventually we'll be able to compile the compiler with itself. Eventually, we'll see how it goes. All right, so one of the things I probably want to do is probably take str equal and put it to the standard library, because why not? Right, because we already have things like strlen, right? Why not have str equal? I think it's going to be useful. I think it's going to be rather useful. Okay. So implement subcommands for Porth. Alright, so I'm already streaming for almost 2 hours, and I think today was a pretty productive stream, not gonna lie, holy shit. We already like developed like a, you know, the initial skeleton of the compiler, so we just have to fill in some things. I guess the next big feature is going to be like actually reading and parsing the source code. Luckily, we don't really have that much of a syntax, so we can just read the whole file and split it by words and just basically translate each individual word into an operation. And yeah, and that way we're gonna have like a very small subset of Porth implemented in Porth, and then we're gonna just expand that subset until we expand it to the whole Porth. So, yep. Does anyone have any questions? Okay. Does anyone have any topic? I was coding in Porth for fun, and why is there and or not but not Zor? Because I never needed it, and I only add operations that I need. So once I need Zor, I'll implement it. So the compiler is not finished yet, so I'm sorry. So... Okay. How about using LLVM for compiling? No, we're not going to be using LLVM for compiling. It might be interesting to keep the log of which unhandled data there is left, where it's coming from. Type checking. I'm not sure what you mean by that. I'm sorry. What will you have for bootstrapping? Okay, this is actually a good question. So eventually we're going to get rid of the Python, right? And the question is what we're going to use for the bootstrapping. So the thing is, our compiler generates assembly, right? So for bootstrapping, we're going to keep the assembly version of the compiler along with the Porth version of the compiler. So to bootstrap the compiler, you will only need NASM, right? So once the Porth is finished, we're gonna simply commit porth.asm along with porth.porth, right? So, and then on the platform on which you need Porth, you would just only need NASM. You would compile Porth with NASM, and this is how you would bootstrap. Does it make sense? This is actually a pretty good question, thank you. And as we add more platforms, right, we're gonna add more files for different platforms, right? So then we're gonna have ARM, 64. Then we may have WebAssembly support, and for all of these things, we're gonna have like separate files that you can just bootstrap the Porth from. So yeah, that's how we're gonna be bootstrapping this entire thing. All right. So I guess that's it for today. Thanks everyone who's watching me right now. I really appreciate it. Have a good one, and I see you on the next Debugging session. Check out all of the links in the description that I left. You can find the source code in here. If you're watching live, check out the source code in here. Yeah, I suppose I gotta go. So maybe we should rate somebody. I don't know. Every time I try to rate somebody, nobody is streaming anything interesting. So let me see. Oh my god, it's so slow. So slow. I don't know. So who are those people? Who's that? I don't remember this person. Nothing changed. Okay. Cool. Thanks for the stream. You're welcome. Thank you for watching. John Blow is doing something. New rewind UI. I don't know. I guess I'm gonna go watch John Blow after the stream, so might as well redirect all of you there. Is John Blow doing something interesting? Something cool? Something about UI. He's probably continue developing his like UI framework that will come with his language or something. So let's actually rage Blow. So what was that? We got a subscriber. Dredge, I hope I pronounced your nickname correct. Thank you so much for 3 months of tier 1 subscription. Thank you. I wish Twitch was a little bit faster. Blow. Alright. Get ready for the raid, boys and girls. Get ready for the raid. And I see you all next time. Thank you for all of the support. Love you all. Mwah.